So our job today is going to be to implement the LRU cache, and LRU stands for least recently used. So it's a cache that works just like any other cache, but when it comes time to evict its entries, it's going to start by evicting the least recently used entry. The LRU cache is going to be initialized with a certain capacity. So maybe the capacity is like 3 or something, in which case the cache can only hold 3 entries. The first method that we have to implement is going to be the get method, and the get method is pretty straightforward. It just returns the value corresponding to the key. So if our cache has like 1, 10, if I call the get function with the key 1, then it should give me the value 10. Pretty straightforward. If it doesn't exist, then return -1. Then the next thing that we have to implement is the put function. And the put function basically has 2 possibilities. The first possibility is that if the key already exists in the cache, so for example, if I call put 1, 15, then I have to update the value from 10 to 15. Otherwise, if I do like a put to 20, because 2 doesn't exist in the cache, we have to add 2 to our cache. And for this last line, we can see that if, let's say, our capacity is 2 in total, right? And now we're to try to insert another value here. If by introducing this new pair, it would cause the cache to exceed the capacity of 2, then we need to remove the least recently used key. So what does it mean for a key to be most recently used? Well, a key is considered used if a get or put operation is called on it. So if I have a separate data structure, I'm just going to use a generic list right now. In the very beginning, we inserted 1, and then we inserted 2, right? So this is currently our least recently used entry. So if we were trying to insert the key 3, then we would have to evict this one. However, if before this I were to call like get 1, for example, or if I were to call put 1 like 20 or something, and I'm updating the value of 1, then our 1 would become our most recently used entry, right? And that would be our MRU. Anything on the rightmost unit is going to be an MRU, and anything on our leftmost is going to be our LRU, least recently used. So this algorithm would instead delete the entry 2 instead from both the data structure that keeps track of the most recently used elements as well as the cache before putting in 3 in here, right? And for the last part, we have to ensure that get and put run in O1 time. So using a list to keep track of the least and most recently units wouldn't really work. And that's because, well, let's go back to our original state. 1, 2, let's our capacity is 3, okay? It was initialized with 3, and so this push would go through, right? And this would be our 3rd unit. Now, I'm gonna call get 2, right? And as we can see, our number 2 is in the middle of the list. And if you imagine if our list was really long, our number 2 is kind of like nestled like in between here somewhere. We don't really know where it is for sure. So if I want to bump our number 2 to the most recently used here, it's going to cost me O of n to find the number 2 before deleting this and moving it there. So it's quite bad. We have to think of a proper data structure to be able to accomplish this in O1 time. Okay, so what do we do? Okay, now the problem we were having was that if we wanted to bump a value from somewhere in here to the very front of the list, then it would be an O of n search. So like in our gets or our puts and whatnot, right? So given a key, we want to be able to find the position of it inside a list. So why don't we use a linked list to represent our history? So instead of having our cache point to the number directly, why don't we have it point to a node instead, right? So our history would look like this. It's going to be a linked list, right? So if I get a get request for the key of 2, then I can look it up in our cache, get the reference of this node, and immediately be able to access this. So if I know the previous element, then I can delete this link, point it here, and then have the next node here point to our node 20, and our node 20 will point to null. And there you go. Our node has been bumped successfully. Now, one thing that you notice with this is that in order for us to remove a node, we need access to the previous node, right? So instead of just having 2 point to our 20 node, well, I'm just going to call this node, right? We also need a pointer that goes to the previous node. And so every single entry would need a prev and like the node itself. However, that does make the code a little more cluttered, and there's frankly a better way to do this. And that would be to use a doubly linked list. So in a doubly linked list, each node, as we know, has a previous attribute as well as the usual next and value. So our 20 here would also have a previous pointer pointing to the 10, and our 30 would have a previous pointer pointing to the 20, and of course 10 and 30 both point to null respectively, right? So that's really convenient. So if we set up our data structure to use a doubly linked list, we don't have to keep track of 2 nodes per entry in the cache. So let's do that. And another thing that I want to mention is that I'm sure you're already familiar with singly linked lists. And in singly linked lists, in the beginning, our linked list is none, right? And if we want to append an element to it, we need to do like an if check, right? Like if, let's say this is head. If head is not none, then we can do like head dot append node, right? And otherwise, we just set head to the node. And this can get really annoying. Sorry, I meant like head.next here. And you know, this is going to give us a null pointer exception, right? And the way we solve that is by having a dummy node that we put in the beginning. So instead of pointing head to none in the beginning, we create a dummy node. So even from the very start, we can do things like head.next is equal to blah, 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 right? So we don't have to do those really annoying if checks again. And the idea is kind of the same in a doubly linked list. So removal in the normal case would be really easy. I take this link and I point it here. I take this link and then I point it here, and then this node is removed, right? But think about what happens if I try to remove this node. I sever this, point this to null, and then obviously null doesn't have a previous pointer. So when I do this node dot prev, it's also gonna error. So the solution to that is to have two dummy nodes, one in the front and one in the back. So I'm gonna call this my left node, and then this is gonna be my right node. And this is going to help us simplify our code a lot. So let's get back to it. So let's start with the logic for get, since it's the easiest one. So get gives us a key, and then if key not in cache, then we return -1, right? So we have to do three things here. The first one, let's say the key is 2. I need to delete this from my cache, and then I need to delete this, and then I need to append it in the very front. So let's see what that might look like. So let's get the node first. We're going to get it from my cache, pass in the key, and then now we have a reference to this node, which is nice. Then I need to remove this node and I need to append it. Then I return node.val. Simple. Well, obviously we have to define these two functions. So let's go. For the removal, we're going to be given a node and we need access to the previous and the next node. So we need this and we need this. Okay, that's pretty easy. It's going to be node.prev and node.next. And all we're doing is our prev.next, that's going to be equal to next. So this should be going here. And then the other thing is the next.prev should be equal to prev, right? This one should point to this one. So ultimately, this would sever any incoming links going to our node here. So that would be our removal, like so. Let me just draw this properly. There you go. And right now our 20 is still a little bit cucked, but that's okay. Oh, also, these left and right nodes also point to the insides. Right, okay, so 20 has been removed, and then we must append 20. Let's go to find append. So if you imagine, 20 is going to be inserted here, right? So the prev is going to be 30, and the next is going to be this right node here. So let's go to find the prev and the next. That's going to be equal to right.prev, that's this guy here, and then the next is going to be the right node itself. All right, so let's fix up the links. Prev.next is going to be equal to next.prev. So that will be these two links here. That value is going to be equal to node. So our node 20 here is going to get sandwiched in between these two nodes. And the prev.next is going to be pointing to 20, and the next.prev is going to be pointing to 20. There we go. And then we have to fix the outgoing connections as well. So node.prev and node.next is equal to prev and next. Right, this points here, this points here. And that is the bump operation completed. The pointer manipulation and stuff like that can be pretty messy, so I think it's really good that we abstracted those away into their own little functions. Now, what about our put? Well, our put has two branching paths. Remember, the first scenario is if, well, first of all, put takes in a key and a value. If key is in the cache, then we want to update the value, and then we also want to bump it up. So updating the value is pretty trivial. All we do is get the node and then just update the value to whatever it is we were passed in. And then the bumping's also really easy. We've done this before. We remove the node and then we append it to the end of the list. Now, what's more interesting is going to be the second path. What do we do when the key is not in the cache? Well, then we want to insert the key, right? But before inserting the key, we have to make sure that the cache still has space. So if cache is full, then we want to evict LRU, right? So checking the cache is full is not that hard. We take the length of the cache, and if it's greater than or equal to our capacity, then we want to evict. Evicting's also surprisingly simple. So our LRU is going to be equal to left.next, right? That's this node here. Then we can just run the remove function on our LRU node. That's going to sever this connection, and that's going to sever this connection, effectively removing it from the list. And after that, we just get rid of it from our cache, right? However, we need the key of the node that we're removing. So we know that 10 corresponds to 1, but our data structure doesn't show that, which is why every node needs to keep track of both the key and the value. So this node needs to keep track of 110, this one keeps track of 220, this one keeps track of 330. So these are 330, 220, right? So if we do that, then hey, it's really easy. All we have to do is delete cache, and the key is going to be the LRU dot key, and that's going to give us the number 1, which we can evict from our cache. Really easy. And then now we can safely add the new value. Let's say we're adding 4 and 40. So we need to create the new node object, pass in the key, pass in the value, then we add it to the cache equals to node, and then we just append our node. And that's going to conveniently put our node here. And we would also have an entry for it. Connections and write. And that should cover all of it. So as you can see, our data structure is really important. Having this doubly linked lists and our left and right sentinels here, as well as our node type. Forgot to write that down. Our node type needs to have a key, a value, a previous, and a next. And I think that's all we need to know. So first of all, let's start with the node class that has the properties that I mentioned before. And then in our inits, of course, we need the capacity and the cache, as well as the left and right nodes. But right now they're not pointing to anything. And in the beginning, we want to point the left to the right and the right to the left. So let's do that. Once that's done, then we need to define our remove function, which disconnects the incoming connection from the previous and the next node to our target node. The next function would be our append function. This is going to point the previous and the next node to our node here, and then it'll point the previous and next of our node to the node in front and the node in the back. And then this is a lot of setup, but the rest of the code is not too bad. For a get function, we return -1 if the key is not in our cache. If it is in our cache, then we grab the node, and then we remove that node from wherever it is, and then we append that node in the very front. Once we've bumped it up to become our MRU, we're going to return the value of the node. Next, for our put function, we have 2 different paths. One is if the key is inside the cache, and another path if it isn't. If it is in the cache, then we need to update the value of the node and then bump it up. In the else clause, we want to check if our cache is at capacity. If it's at capacity, then we want to remove the LRU node from our linked list and then delete it from the cache. And then now we can safely insert our new entry. So we create a new node, append it to our linked list, and then add it to our cache. And that's pretty much it. Let's give it a run. And there you go. Remove and append. Everything's pretty much O1 at this point. For our remove and append functions, all they do is redirect some pointers. So these are O1. And for everything else, we just have dictionary lookups or dictionary deletions. And as for the space complexity, we are keeping track of a cache. So naturally, that's going to be O of, well, the size of capacity, right? Our cache can only grow so much. And our linked list is going to be used to store our elements in order from least to most recently used, which is going to be O of capacity. And that's about it. Thanks for watching. Okay, bye.